Hello everyone, my name is Hassan Negatu. In this presentation, I'm going to talk about the formulation of dimensionally homogeneous Jacobian using extended selection matrix for performance evaluation and optimization of parallel manipulator. Here is the content. I will first introduce the basic, discuss the existing problem, present the proposed solution, and discuss the demonstrative example, and finally conclude. The performance evaluation of parallel manipulator plays an important role in ensuring the optimal quality and quantity of their workspace. Usually the performances are measured using indexes such as condition number, manipulability, minimum singular value, power coefficient, and etc. When the Jacobian is employed to compute the performance of the manipulator and the manipulator has a mixed degrees of freedom, those indexes such as condition number, manipulability, and minimum singular value cannot be used to properly measure the performance due to the unit inconsistency. If we look at this Jacobian that relates the task velocity to the actuated joint velocity, the first term is unit loss, while the second term has a unit of length. Because of this translational inconsistency, the condition number and manipulability as well as the minimum singular values cannot properly measure the performance of the manipulators. In order to solve this problem, researchers proposed dimensionally homogeneous Jacobian as a widely used method to solve this problem. So, characteristic length approach and point-based approach are most commonly used techniques to derive the dimensional homogeneous Jacobian. The characteristic length is used to divide the second term of the Jacobian to remove the unit meter from this term. So the dimension of this Jacobian becomes consistent and suitable to compute the performance indexes. However, the geometric interpretation of characteristic length is not clear in this case. The second method is point-based approach, and in this approach, the motion of the moving plate is represented with the pointers velocities. Those pointers are selected on the moving plate in the non-collinear manner, and then this velocities, pointers velocity is related to the moving velocity with this shifting property. Therefore, when we have multiple pointers on the moving plate to represent its motion, their velocity can be related to the center velocity by using this relation. So this is a point velocity, this is a mapping matrix, and this is a moving plate center velocity. So as can be seen from the equation, each point has three components, but not all components are independent. In order to represent the motion of the moving plate, we need to use independent component velocities, and those independent component velocities must be chosen via selection matrix. Therefore, selection matrix selects the linear velocity components from the designated pointers that fully represent the motion of the moving plate. Therefore, selection matrix is derived from the shifting property equation that we can see here. If we look at the components in detail, the component Vix fully represents the motion of the moving plate when it has the motion of x translation and yz rotation. Similarly, the y component can represent when the manipulator has y translation and xz rotation. If we take the manipulator that has a z translation and xy rotation as an instance, the selection matrix can be established this way with zeros and ones, which we call it usual selection matrix. And this usual selection matrix comprises only zeros and ones to pick the independent terms from the z component and remove the remaining unwanted task velocities. So by multiplying the pointers velocities with the selection matrix, we can obtain the relationship between independent components of the point that represent the motion of the moving plate with the Cartesian velocity. And from the forward rate kinematic relation, we have the task velocity and actuated joint velocity relation. So by combining this, we can obtain the relationship between selected independent component and actuated joint velocity, and that Jacobian that relates those two terms is called dimensional homogeneous Jacobian, which has a dimension of 3 by 3 in this particular case. However, when the parallel manipulator is different from these three manipulators, the selection matrix combines components from different pointers to fully describe the motion of the moving plate, because the components cannot independently represent the motion of the moving plate. For example, if the manipulator has the x translation, rotation, x rotation, and z rotation, Vix component only comprises comprises Vx and Wz. VII component comprises only Wx and Wz. So by combining Vix and Viy, we can fully represent the motion of the moving plate with a linear velocity, with a condition that removes Wy and Wy from the system. Hence, the usual selection matrix in this case is not valid anymore. Thus, we propose the extended selection matrix. The velocity of pointers obtained by combining different components from the point is called nominal velocity, and the dimensionally homogeneous Jacobian relates this nominal velocity of the moving plate with the actuator rate. Here is the flow chart that demonstrates the entire process. So first we drive the rate kinematics with the constraint embedded in it, and then obtain the independent point component velocities from the moving plate. So in order to represent the motion of the moving plate with the point's linear velocity, we have to pick sufficient non-collinear points on the moving plate and then drive the velocity, the linear velocity of those pointers. And then we have to check if the manipulator is different from these three type of specific manipulators. If yes, we have to use the usual selection matrix. If no, we have to apply the extended selection matrix. After we obtain the selection matrix, then we combine this equation with the forward brake kinematic equation to get the dimensionally homogeneous Jacobian that relates the linear velocity with the actuator joint velocity. So in order to demonstrate this proposed approach, we use the 4 degrees of freedom parallel manipulator shown here. This 4 degrees of freedom parallel manipulator has two PUS limbs and 2 PRS limbs. Because of this limb arrangement, the manipulator has YZ translation and XY rotation. Therefore, the components, independent components of the point's velocity cannot represent the motion of the moving plate. In order to fully represent, we have to combine different points. So in this manipulator, because it has 4 degrees of freedom, to fully represent the motion of a moving plate, we need at least 4 non-collinear pointers distributed on the moving plate. In this case, we take those 4 pointers at the center of the joints on the moving plate, and those points velocity is related to the task velocity with the matrix Vp, which has the dimension of 12 by 6. From the component velocities, we can clearly see that component Viy and component Viz can fully describe the motion of the moving plate. If we combine these two components from different pointers, we can fully describe the motion of the moving plate. And the combination is not unique, so for each limb relation with the point's velocity, we can have 3 candidate combinations. And for 4 limbs in total, we will have 12 different combinations, and we can take any of those combinations to represent the moving plate velocity with linear velocity. And in this particular case, we take this combination, and by arranging this relation for the 4 pointers to remove, with the condition that can remove the X translation and Z rotation from the equation, we can establish the selection matrix. So with this final equation, we have the relationship between the nominal velocity of the moving plate, which obtained by combining different pointers to the Cartesian velocity, and this is the appropriate dimension of the equation. So this is the selection matrix that removes the unwanted or undesired task velocity components and retains the independent ones by establishing the relationship between nominal velocity and independent task velocity. As we can see here, this selection matrix comprises different coefficients than the usual selection matrix. That those coefficients are used to remove the unwanted moving plate velocities and retain the dependent velocities. By using this selection matrix, we can establish the relationship between nominal velocity and independent task velocity of the moving plate. And we can see that the nominal velocity is a combination of Viy and Viz with the coefficient that removes undesired motion. So here is the inverse Jacobian. The first 4 terms are the motion Jacobian, while the last 2 terms are constraints. And here are the forward Jacobian that relates task velocity to the actuator joint velocity. Substituting this relation, we get the nominal velocity relation with the Cartesian velocity, and then eventually by substituting this forward relation into this nominal velocity equation, we get the dimensional homogeneous Jacobian, which is 4 by 4. And to prove the dimensional homogeneity of the Jacobian, we have the relation between Cartesian velocity and point velocity. This matrix has that maps the two velocities has unit of length on the second term, and the first term is unitless. And the extended selection matrix is unitless as usual selection matrix. For the manipulator with a linear actuator, GAV and GCV are dimensionless, while GAW and GCW are unit of length. So we can analytically derive the inverse, the forward Jacobian, and we know that the second term is unit of length, while the first term is unitless. So by multiplying these two, we get the dimensionless dimensional homogeneous Jacobian. For manipulators with rotational actuators, GAV and GCV have unit of length, while GAW and GCW are dimensionless. So by multiplying this relation with this one, we get the Jacobian that has unit of length, which is consistent. In order to demonstrate the validity of the approach, we took this the numerical example with the following structural and post parameters. So first, we calculate the condition number distribution over the entire workspace using the conventional Jacobian with the unit millimeter. So as can be seen here, the condition number distribution condition number has a very large value compared to the ideal value, which is 1. And then we change the unit of the same Jacobian, and the condition number distribution is different. So it's difficult to compare the performance because of these differences. However, with the proposed Jacobian, the unit variation cannot change the distribution of the condition number over the entire workspace. Therefore, when we change the unit from millimeter to meter, the value remains the same, and the value is also very close to the ideal value, which is 1. Similarly, we said that we can take different combinations. So in here, we took different combinations and obtained different selection matrix. And again, by applying this selection matrix on the component velocities, we obtain a new dimensional homogeneous Jacobian. And we calculate the condition number distribution again here, and the value gives the same result without, it's proven that we can use any of those combinations. So in this work, we introduce extended selection matrix to formulate point-based dimensional homogeneous Jacobian for various constraint parallel manipulators, and the method enables the utilization of the derived Jacobian condition number and singular value as performance indexes for optimization with unit independency. And we check the k-value distribution by changing the units from meter to millimeter, and the derived and for the derived and conventional Jacobians, the derived Jacobian k remains consistent across the unit changes. Therefore, the method enables the correct optimization of wider variety of parallel manipulators with mixed degrees of freedom.